Hey students, welcome to lecture number 13 of Linear Algebra 2. So today we want to continue on talking about linear differential equations. So these we introduced last time as follows. So first we introduced a linear differential operator, which was a map from the space of smooth functions to the space of smooth functions. And we said such a map is a linear differential operator of order n if it sends the function f to a sum like this, where a0 up to an are real numbers and an is not 0, and then it sends f to a0 times the function f itself, plus a1 times the first derivative, up to an times the nth derivative of this function f. And this gives again a smooth function. And then a linear differential equation was an equation like this. So for a given function g, we ask, and for a given linear differential operator t, we ask which functions f satisfy this equation here. So if we apply this differential operator t to f, such that this gives g. And then we saw that to solve such a linear differential equation, what we need to do is we need to find one particular solution. So we need to find one solution which satisfies this equation. And then we can get all solutions by adding elements in the kernel of this linear map t. In other words, solutions to this homogeneous equation, which just means that tf equals 0. And with this, we get all solutions, and therefore the main goal is to understand the kernel of these linear maps. So this is the goal. And so recall that we had this theorem 6.4, which stated that if we have a linear differential operator of order n, then the dimension of this kernel is exactly n. But this theorem we didn't prove yet, and this will be one part of today's lecture to prove this theorem. But since we just talked about real vector spaces in this lecture, we will just give a sketch of proof for this statement here, because we also need complex numbers to actually prove this. But last time we considered a special case where we could write down all elements in the kernel of this differential operator t, in the case when t had a special shape. But first we introduced this so-called characteristic polynomial of t. So if t is given by this sum here, then we defined the characteristic polynomial for t, denoted by pt, to be this polynomial here, where we just write these ai in front of these polynomial x to the I. And then the statement was that if this polynomial has n different zeros, then the function, which are called lambda 1 up to lambda n, then these functions e to the lambda n 1t up to e to the lambda nt, this gives the basis of the kernel t. So in this case we found n linearly independent functions which are elements in the kernel, or in other words, which solves this homogeneous differential equation. So in this case, this pt had a special shape, namely it has a form like this. Maybe there's some number here in front, but the zeros are given by lambda 1 up to x minus lambda n. And all these lambdas are different. So this is a condition here. But of course, not every polynomial has this shape. And today we want to see what happens if the polynomial not just has this shape like this, but maybe also we have some powers here, meaning this 0 here has some multiplicity. But also we know that if we just allow real numbers, then not every real polynomial can be written like this. But the general form of a polynomial with real coefficients is the following. So any real polynomial p can be written like this. So we can have some real number c, which is basically the coefficient of x to the n. And then we have a product here of polynomials p1 up to pr, raised to some power m1 to mr. And these factors can have two different forms. So they could either be a factor like this, like we saw in the example before. So x minus lambda j. So this means that this lambda j is a 0 of this polynomial p. And then we could raise it to some power. This would be the multiplicity of this 0. But also we know that there are some polynomials which don't have any real zeros. But you will maybe see in complex analysis or in calculus that that at least we can factor this real polynomial here, where these building blocks are either these linear terms or these quadratic terms. So here, this polynomial here has no real zeros, because we see that this is positive and this is positive. So no matter what real number I choose here for x, this is not 0 if b is not 0. And so here this b is greater than 0. But if we are allowed to use complex numbers, then we see that this actually has zeros, as we will see later. But the main point here is that we can write any polynomial in a unique way as a polynomial, as a product like this, if we assume that all these different lambdas are different. So, for example, the polynomial x squared plus 1. This is of this type here, and this doesn't have any real zeros. So here in this case, we understood the kernel of the operator t, if its characteristic polynomial has this shape here. But in general, we have a shape like this. So we might ask, how do we determine the kernel of this differential operator if the characteristic polynomial has a factor like this quadratic factor here, or if we raise this factor here to some power m. And we will start by dealing with this case and then later do this case. But for this case here, we will need some complex numbers. But for this, we actually don't need complex numbers. But before we do this, let me do one lemma, which we also could have done last time. So the statement is that if we have two differential operator t1 and t2, then if I apply the operator t2 first and then t1, this is the same as applying t1 first and then t2. So recall this circle here just means a concatenation of functions. So, and why is this important for us? So, for example, consider this differential operator here. Recall this d was a function which just sends f to its derivative. And d squared, for example, just means that we apply d twice. So in other words, d squared sends f to its second derivative, and d cubed sends f to its third derivative. So if we have a differential operator like this, so any differential operator can be written as a sum of powers of these d's. So what is the characteristic polynomial? So in this case, a characteristic polynomial is well, we just need to replace the d's by x, so to say. So x minus 12. And this polynomial we can factor. You can check that this is actually x minus 2 squared times x minus 3. And we can do the same for this differential operator t by saying that this can be factored as d minus 2 squared. And instead of multiplication, we use applying the operator again. So this is a concatenation of functions here, d minus 3. So here, this d minus 2 squared, what we mean by this is that we apply d minus 2 twice. So, and now by this lemma, it doesn't matter in which order we apply these operators. So this means that this is also the same as d minus 3 concatenated with d minus 2 squared, similar to the usual multiplication. And this will be important because now we see that if something is in the kernel of let's say d3, so the kernel of d3, these are all functions such that if I apply d minus 3 to this function, then it's 0. But then, looking at this way of writing t, we see that if we apply t to some function f, then we would apply this d minus 3 first to f, and then this is 0. And no matter what we apply afterwards, this will still be 0, meaning that the kernel of d minus 3, every element in the kernel of d minus 3, in this case, is also in the kernel of t. But if you write it like this way, using this lemma, so we can change the order, we also see that if some element f is in the kernel of this operator, so if we apply this to f, then we get 0, then it's also in the kernel of t, because no matter what we do afterwards, it still be 0, because all these maps are linear maps. So in other words, we also see that the kernel of d minus 2, or the kernel of d minus 2 squared, is also in the kernel of t. Okay, so let's do now one example. So we will be now interested in this question here, and we want to know what happens, what are the elements in the kernel of t if our characteristic polynomial of this operator contains a factor like this, where we have x minus some lambda raised to some power. And the easiest example is the following. So we can consider the case d minus lambda squared. So recall this squared just means applying a d minus lambda twice. So we can write this out. This is this linear differential operator of order 2. So in other words, the characteristic polynomial looks like this. So now we have this case where we have x minus lambda to some power 2 here. And the claim is that in this case we can get two linearly independent elements in the kernel, which are given by this, by e to the lambda t and t times e to the lambda t. And here the statement is that this is the basis of the kernel of t. So in other words, they span the kernel and they are linearly independent. But we already know by theorem 6.4 that in this case the dimension of the kernel is 2, even though we didn't prove this yet, so this will be due at the end. But since we know the dimension of the kernel is 2, we just need to show that these are actually in the kernel and that they are linearly independent, and then we have two linearly independent elements in a space with dimension 2, and therefore it's a basis. So let's see why these two elements are actually in the kernel of this differential operator t. Well, so we need to see what happens if we apply t to these elements. And t, so t is d minus lambda and d minus lambda. So, but already if I apply d minus lambda to the first element here, to this guy, then we already learned that this is in the kernel, because if I take the derivative of this, then I get a factor lambda in front, and minus lambda times this gives 0. So this is 0. So in other words, this the e lambda t is already in the kernel of d minus lambda, and the kernel d minus lambda, as we saw before, is in the kernel of t. Because if I can write t as a product like this, by product I mean applying these operators, the concatenation of functions, then the kernel of these parts are already contained in the kernel of this operator t. But now, why is this guy also in the kernel? So this is now a new element we didn't see before. But let's apply this operator to this function here. So what does this mean? We apply d to this function minus lambda times this function. And so d is just taking the derivative. So what is the derivative of this product here? Well, for this we just use the product rule, meaning we need to take the derivative of t times this function plus the derivative of this times t. But the derivative of t is just 1, so we get e to the lambda t plus, and the derivative of e to the lambda t is lambda times e to the lambda t, and this, if we multiply it with t, we get lambda times t e to the lambda t minus, and still this guy here, so minus e to the lambda t. And here we see that actually this cancels out, and we just have this guy here in the end. And so, but now we just applied this d minus lambda, but this operator t is given by applying d minus lambda, and then again applying d minus lambda. But if we now apply d minus lambda again to this, we see we just apply d minus lambda to this e to the lambda t, but here we already saw that this is 0. So therefore, if we apply it twice, this is the same as applying this to e lambda t, and this is 0. And therefore, t e lambda t is in the kernel of t, because this here is just t. Okay, and why are these two functions are linearly independent? So we just showed that these are actually elements in the kernel, but why they are linearly independent? Well, in this case, it's easy to see because so linearly independent. We have that this, the first element, is in the kernel of d minus lambda, but this element, t e lambda t, is not in the kernel of this operator, because if we apply this operator, we don't get 0, we get this function here. So therefore, this is in this space, but this is not in this space, and therefore these two functions cannot be linearly dependent, because otherwise this would mean that I can write this as a linear combination of this, but this would also mean that this is in the kernel, which is it's not. So they are linearly independent, and therefore they are a basis, because we know the space has dimension 2. Okay, so this was now one special case of this question here. So what happens if we have a term like this? So if this m is 1, we already had this case before. If the m is 1 here, so in this case we always had 1, then we get this function e to the lambda 1t. And now we saw an example where the factor here is 2, and we got two functions, e to the lambda 1t and t times e to the lambda 1t. And this will be true in general. Namely, we have the following theorem. If the characteristic polynomial of some differential operator of order n has this shape like this, meaning we have x minus lambda 1 to m1 up to x minus lambda r to mr, and here the sum of these m's is n if the order of this differential operator is n, because this is the degree of this polynomial. And then the statement is, for each of these factors, we get elements in the kernel which look like this. So for one of these factors, I get m linearly independent functions. So I get e to the lambda jt. So the factor x minus lambda j mj gives these mj functions here, where I start with e to the lambda jt, t times e to the lambda jt, t squared times e to the lambda jt, up to t to the mj minus 1 lambda jt. So in total, for each of these factors, for this I get m1 different functions, for the next one I get m2, and for the last one I get mr. So in total I get n linearly independent functions, and then the statement is, if I collect all of these functions here for each of these terms, then this gives a basis of the kernel of t. So again here we just need to show two things, namely that these are actually in the kernel, and that they are linearly independent, because by this theorem 6.4 we know that the dimension of the kernel is n, and here we have a list of n functions. Okay, so proof sketch, because we will just show that these are actually elements in the kernel, and then linearly independence we will skip, and you can do it for yourself. So let's see what happens if I apply the differential operator d minus lambda to, let's say, a function of this type here. So these functions always have a form that t to the something times e to the lambda t. So let's say I have t to the n e to the lambda t, and I apply now this differential operator d minus lambda to this. So it would be more correct to say like this. So as before, this means I take the derivative of this minus lambda times this function. But now again, as similar as in the example, we can now do use the product rule to take the derivative of this. So meaning we need to take the derivative of t to the n, which is n times t to the n minus 1 e to the lambda t plus, and then take the derivative of e to the lambda t. So lambda times t to the n e lambda t minus lambda t to the n e lambda t. And again, here this part cancels out. So we see that we just have this term here, n times t to the n minus 1 e to the lambda t. So if we apply this operator d to the d minus lambda to t to the n e to the lambda t, what we get is n times this term, but we decrease this exponent here by 1. Similar to the example where we had t to the 1 here, and then here in the end we had t to the 0. And then we saw this was then in the kernel of this map here, because we know that if we apply d minus lambda to this, we get 0. But the same strategy holds here now, because if I now would apply d minus lambda again to this, then I would again decrease this exponent here, and I can apply this m times, and then we'll see that this will be 0, because in the last step I will just have e to the lambda t, and if I apply d minus lambda to this, this will be 0. So inductively, we see that these elements, let's say lambda jt, t e lambda jt, up to mj minus 1 e to the lambda jt, they are all in the kernel of d minus lambda j to the mj. And so I mean, this is already in the kernel of d minus lambda j, this is in the kernel of d minus lambda j squared, and this here is in the kernel of d minus lambda j to the mj, but all of them are in the kernel of d minus lambda j to the mj. And with the same argument as before, these are linearly independent. And so now, because t, so what is our operator t? It's d minus lambda 1 to m1 up to d minus lambda r, mr. And because these are in the kernel of one of these factors, because the order doesn't matter, we also see that they are in the kernel of t, because all of these, the kernels of these factors are in the kernel of t. And therefore these are also elements in the kernel of t. So for each j, these functions are in the kernel of t. And for a fixed j, they are also linearly independent. And then it just remains to show that for different j's, they are also linearly independent, but this we will check, this we will skip here. So this you can check by yourself. But then by theorem 6.4, we have that the kernel, the dimension of the kernel is n, where n is the sum of these m's, and therefore we get it that this b here, the collection of all these functions, because we have n linearly independent functions, this is the basis of the kernel of t. Yes, so this is the theorem here. So this answers the question, the left-hand side of this question. So what happens if the kernel, if the characteristic polynomial has a factor like this, and this, so this here is a polynomial of degree m, x minus lambda to the m, and the statement is that we get m linearly independent functions in the kernel of t, given by e to the lambda t, t times e to the lambda t, up to t to the m minus 1 e to the lambda t. So each of these factors gives m functions in the kernel of t. Okay, so let's do one example before we go to the right-hand side of the question. So, for example, if we have the differential operator given by this, so we ask for the solutions of this homogeneous differential equation here. So t is d cubed minus 3 times d plus 2. And this can be factored like this. So here, I don't write it always, but this is not the multiplication, this is the concatenation of functions. And then by this theorem, so what are the lambdas here? So here, lambda 1 is 1, and lambda 2 is minus 2, and m1 is 2, and m2 is 1. So because we have a 1 here. And then the statement by the theorem is that we get, for this term, we get two linearly independent functions given by e to the lambda 1 times t and t times e to the lambda 1 times t. So this comes from this factor, and for this we get this one function here. So in total we get 3 linearly independent functions, and we have a differential operator of order 3. And then the solutions to this equation here, to this homogeneous equation, are given as follows. So this f is then the linear combination of these 3 functions. Oops, there's a t plus 3t. Okay, so what happens if our characteristic polynomial has a factor like this, x minus a plus b, where this b is now positive? So this means we cannot write this as x minus lambda 1 times x minus lambda 2. But what we will see now is this has degree 2, but this will also give us 2 linearly independent functions. So one will be e to the at cosine of bt, and the other one will be e to the at sine of bt. And then we will also see that if we multiply it with, if we take it to the mth power, then we will also have t to the j here, where j runs from 0 to m minus 1. So in total, this factor here of degree 2m will give us exactly 2m linearly independent functions. But for this we will need to use complex numbers. So, but first let's write down the exact statement. So let's assume we have a differential operator t, and the characteristic polynomial has a factor of this form here, x minus a squared plus b squared, and I should always say b is greater than 0, to the power m. Then these functions here, e at cosine bt, e to the at times sine bt, so these are 2 functions, and then I can multiply it with t, both of these functions, so up to, I can multiply them with 2 to the m minus 1, and therefore in total I have 2m linearly independent elements in the kernel of t. And this number of elements corresponds to the degree of this polynomial. So what is the idea behind this? So again, sketch of the proof. So now we need to use complex numbers and then use the same argument as before. So for this, this x minus a squared plus b squared, this can actually be written as x minus lambda times x minus lambda bar, where these lambdas are not real numbers anymore, but so maybe I should, where this lambda is a plus bi, where I is now the complex number, which is, if you square it, it's minus 1, so it's a square root of minus 1. And lambda bar is the so-called complex conjugate, which just means instead of plus, I write a minus here. And then you can check that in general, if I have a complex number lambda and I multiply it with lambda bar, so this is a plus bi, a minus bi, so this is a squared plus bi squared, minus. So this is just if you multiply it in the usual way, but I squared is minus 1, and therefore this is a squared plus b squared. And using this, if you multiply this out here, then you see that you get exactly this expression here. So in other words, if we are allowed to use complex numbers, then this polynomial of degree 2 can again be written as x minus lambda 1 and lambda 2. So we can use the same idea as before. So the statement is that this theorem here is actually true if we allow these lambdas to be complex numbers, and then any real polynomial can be written like this here, where these lambdas now come in pairs given by lambda and their complex conjugates. And the statement is we get linearly independent functions or elements in the kernel. So maybe first we want this to the power m, here m, so here we get m. And for this term here we have the same elements again. It's e to the lambda t times e to the lambda t up to t to the m minus 1 e to the lambda t. And for this term here we have e to the lambda bar t e to the lambda bar t up to t m minus 1 e to the lambda bar t. So these are 2m elements, and these are also in the kernel of t. But how do we go now to these sine and cosine? I mean, now we have these exponential functions as before, but now these lambdas are complex numbers, and what we actually want to get are real functions. So if I plug in a real number here for t, and lambda is complex, then this will also give a complex number. So these functions are actually not in the space of smooth functions from the real numbers to the real numbers, but we can combine them such that we get these cosines and sines. And for this we know we use the following formula, which is due to Leonhard Euler, which states that in general, if I take e to the ix, where x is now a real number, then this is cosine of x plus I times the sine of x. And so therefore, if I now look at these functions here, what is e to the lambda t? So lambda is a plus bi, so this is e to the a plus bi t, and therefore this is e to the at e to the b ti. And now we can use Euler and see that this is the cosine of bt plus I times the sine of bt. And the same I can do for the complex conjugate, e to the lambda bar t. So this is e to the a minus bit. This is eat, e minus bti, eat. So now here we would have the cosine of minus bt, but the cosine goes like this. So the cosine of minus x is the same as the cosine of x, because it's an even function. So therefore the cosine of minus bt is the same as the cosine of bt. And now here we would have the sine of minus bt, but the sine is an odd function, meaning that the value at x is the negative value at minus x. Therefore, if we plug in minus bt, we get this is minus I sine of bt. Okay, and now we see that, we could also multiply everything with t to the power of some n. Well, maybe we do it in the next step. And now we can see that we can combine these two functions to just get the cosine or the sine. So for example, if I add this one here to this one, then we see that these these parts cancel out because here's a different sign. So I get 2 times this part here. So if I multiply it by 1/2, I have exactly this part here. And if I take this one and I subtract this one, then we see that I have 2 times this part here, and this part cancels out. So what we can do is we see that t to the n, so we get at cosine of bt. So this is what I said before. So this tn we just multiply in front to get these functions here. Oops, where am I? So we have these functions with some t in front. And then I take 1/2 of the sum of these two. So I take e to the lambda t plus e to the lambda bar t. Because if I add them, this cancels out and I have 2 times this cosine, and therefore if I take 1/2, I just have this part here. And if I do the same, so if I want to get the sine out of this, I can subtract them. And if I subtract this from this, I get 2i sine of this. So if I multiply it with minus I get just the sine. And if I take 1/2 and t to the n, so this cosine cancels out, we get exactly this part here. So in other words, these complex functions, we can combine them in a way such that we get actually real functions. So these here, if I plug in real numbers for t, I will also get a real number. So the right hand side, these are really functions again in C infinity, where these functions here are in actually, so the values would be in the space of complex numbers. And you can also check that if these are linearly independent, then also these functions here are linearly independent, because what we basically did is we just made a change of basis in this space spanned by these functions here, because you can see that if you want to go back, you could combine these again to get these functions. So this is just a change of basis in this space here, and this gives us a family of linearly independent functions, and in total we get exactly 2m linearly independent elements in the kernel of T. And yes, and this is what the statement of this theorem is. So let me recap here. Let's go back to the question. Yeah, so this part here we did before, and now we did this part here, b is greater than 0. And the statement here that this gives us 2 functions, the cosine and the sine. And if we take it to some power m, we also have these t to the j in front. So in total this factor also gives 2m functions, and this factor here gives an m function. So the number of functions we get in this kernel corresponds to the degree. So in total, if we have a polynomial like this, which has a degree which is given by the sum of the degrees of these factors, then we get now exactly n linearly independent functions in the kernel. Okay. And now, so this is this. And now we want to show that this theorem 6.4, where the statement was that the dimension of the kernel is exactly given by the order of the differential operator. But for this we first need to prove a general statement on linear maps. So our differential operators are linear maps, and to prove our theorem 6.4 we need this lemma here. So let f and g be 2 linear maps between vector spaces u, v and w. So I have u, v and w, and f is a map from u to v, and g is a map from v to w, and we assume that they are surjective, meaning that for any element in v I can find an element in u such that f of this element u maps to this element in v. And the statement of the theorem is that if the kernel of these linear maps, so the kernel of f lives in here and the kernel of G lives in here, so if they are finally generated, then the dimension of the kernel of f, the dimension of this, plus the dimension of this, equals the dimension of the concatenation of these maps. So the map G circle f goes from U to W, and the kernel of this also lives in here. And this statement is that the dimension of the kernel of this map equals the dimension of the kernel of this plus the dimension of the kernel of this map. Okay, so let's prove this. So both of these kernels we assume are finally generated, and therefore the kernel of G has we can write down a basis. So we call this V1 up to Vm is a basis of kernel of G. So in other words, we say that the dimension of the kernel of G is given by m because we have m basis elements. So these elements V live here, and because f is surjective, for each of these elements we can find elements in U such that f of these U's gives these V's. So f is surjective, and therefore we can find elements U1 up to Um in U such that f of Uj equals Vj for j going from 1 to m. So the U's are elements here. And now the kernel of f also lives here, and this is also finitely generated, so we can also choose a basis, and we denote these elements by x. So x1 up to xl, we say this is a basis of kernel of f. So in other words, we say that the dimension of the kernel of f is L. And what we want to show to prove this lemma is that the dimension of this kernel is given by L plus m. And the idea to do this is to write down an explicit basis of this kernel with L plus m elements. And the claim is, so now we have L elements here in U and m elements here in U, and the claim is that if we combine these two, this is actually a basis of the kernel of G circle f. So claim x1, xl, u1, um is a basis of the kernel of G circle f. And so for this we need to show that, well, first of all, clearly they are elements in the kernel, but we need to show that they are linearly independent and that they generate this kernel here. So in other words, for any element in the kernel, we need to show that we can write this as a linear combination of these x and u. So therefore we start with some element in the kernel of G circle f. So the y lives here. So if I apply f to y, I get some element here, and if I apply g, I get 0. Therefore, the f of y, which is here, needs to be in the kernel of g, because we know that that it's in the kernel of gf. So this means that f of y, which is now an element in V, this is in the kernel of G. So this is in the kernel of G. And the kernel of G, we say, have a basis V1 up to Vm. Therefore, we can write f of y as linear combination lambda j of Vj. J goes from 1 to m. Okay, and now, so we have this element, so this here is an element here, it's a linear combination of these v's, and now we take the same linear combination, but instead of v's we take u's. So we say set W to be lambda j uj. So this W is also in here. And recall that if we apply f to the u, then we get exactly Vj. So if I apply f to w, I get exactly f of y. And because f is linear, this means that y minus w, if I apply f to this, is 0. Or in other words, y minus w is in the kernel of f. And now the kernel of f has a basis given by these x, and therefore y minus w can be written as a linear combination of these xj with some coefficients mu, so the dimension is L. But this now means that w is a linear combination of these u's, and therefore if we bring w on this side here, what we get is that y is this linear combination of these x plus these linear combinations of the u's. And therefore y can be written as a linear combination of x and u. And this is what we wanted to show, because we wanted to show that these elements x and u, that they generate the kernel of G. And we started with an arbitrary element in the kernel of G circle F, and we started with an arbitrary element in the kernel, and we could write it as a linear combination in terms of x and u. And now why are these elements linearly independent? Well, we need to show that if this here, this an arbitrary linear combination is 0, then we want to show that these coefficients are 0. But so let me steal this here. So let's assume, so we want to show linearly independence. Let's assume that this is 0, and we want to show mu and lambdas are 0 then. So if I apply f to this, so if I apply f to this thing here, then we see that these x are in the kernel, so this vanishes, and I just have f of this, and because f is linear, I can write it down here, so it's f of these, but this would just mean that I get vj's here, and then I have a linear combination of vj's, which is 0, but the vj's are linearly independent, and therefore the lambdas are 0. So we can assume lambdas are 0, and then we ask, we have this equation here, that the linear combination of these xj is 0, but the xj's are also linearly independent, and therefore the mu's are 0. And therefore, if we have an equation like this, then these two are always 0. And therefore they are linearly independent. Okay. And therefore, we have a generating set of this space here. L plus m elements, they are linearly independent, and therefore they are a basis. And therefore the dimension of this here is also m plus L. And therefore m plus L equals m plus L. Okay, so now let's use this lemma for our purpose, because we want to show this theorem 6.4, namely that the dimension of differential operator, the dimension of the kernel of a differential operator of order n is exactly n. And so first assume that our differential operator has the following shape: d minus lambda 1. Well, we can assume that there's also some factor which we can ignore now, because we're interested in the kernel, up to d minus lambda n. So let's start with this case here, and these lambdas are just some real numbers, which can be the same. So we get, for example, if the first 10 lambdas are the same, then we get some factor to the power of 10 here. And this will also be true, so everything we will do is also true for the case when these lambdas are complex numbers, and therefore we will get this theorem. But let's first assume we have this case here. So last time we saw that the differential equation, so if I just have a term like this, so what is the solution of this differential equation here, where g is some arbitrary smooth function? We saw that this always has a solution. So this has a solution for all g in space of smooth functions, given by, so last time we saw that we can choose the element e to the lambda t, and then we take an antiderivative of this function here, where we have e to the minus lambda t g of t dt, because we checked if we take the derivative of this function here minus this function itself, we get back exactly the g. So in other words, this map here, so the linear map, so this is a differential operator, so therefore it's in particular a linear map from the space of smooth function to the space of smooth functions. What we showed is that if we start with some element here, some g, then we can always find an f such that f gets mapped to this function g, because if we apply this function to this f, we get this g. So if we start with a g, we can find this function here inside on this side, in this space here, and therefore if you apply this operator d minus lambda, we get this g. And this means that this map is surjective, because this is exactly the definition of surjectivity, that each element here has, for each element here we can find some element such that applying this map we get this element here. So in other words, this is surjective. And now, so what is the kernel of this map? This we also saw. So the kernel of this map, so in other words, the solution to the homogeneous equation, so if we have 0 here, we saw the only solution is always given by some multiple of e to the lambda t. So the kernel of this is the span of e to the lambda t, and therefore the dimension of this guy is 1. So this differential operator here is the concatenation of surjective maps where the dimension of their kernels are 1. And now we will use this lemma to show that then the dimension of the kernel of t is given by n, because the dimension of these kernels of these factors is 1, and we have n of these factors. And inductively using this lemma, we will see that this is then gives the dimension n, because here if I have, let's write this out. So this is a differential operator, and or maybe so inductively, induction over n, we get that the dimension of the kernel of t is n, because in the n equals 1 case, so if we just have this one thing here, we see that the kernel, the dimension is 1. And now, by induction, we assume that this statement already holds for this differential operator, meaning that the dimension of this kernel is n minus 1. And then by the lemma before, we see here the dimension of the kernel is 1. And if I have the concatenation of two functions, like here, then the dimension of the kernel is given by the sum of these kernels when these maps are surjective. And in this case here, we see that this is actually surjective. So all of these maps are surjective, and therefore, if by the induction hypothesis this has dimension n minus 1 and this has dimension 1, then n minus 1 plus 1 is n, and therefore the dimension of the kernel of t is n. And this proves our theorem. But now we just did it for real numbers, but as I said, this always also works for complex numbers, which we didn't deal with in this course, so therefore this is just a sketch of this proof. But even though we need complex numbers to prove this statement, these functions we obtain in the end as elements in the kernel are actually real functions. So starting with any differential operator of order n, we can always find n linearly independent smooth functions in the kernel of this operator, and therefore the homogeneous linear differential equation to this always has n linearly independent solutions. And to finish this topic, we will do one example given by this so-called pendulum. So what we have here is, as you can see here in the animation, we have some mass attached to some rod. So it's some fixed rod, and it swings like this, and we want to describe the motion of this pendulum. You see that in real life, if I do this, then it will stop after some time because of friction. But we now first assume that there's no friction, and then similar as in this animation here, it will swing infinitely. And we want to describe the motion of this, and more precisely what we want to describe is we want to give a function which describes the angle, which is here in this picture here, and depending on the time. So we denote this by theta t, which gives the angle at time t. Okay, so what is the position at time t? So if we look here, so first we have some ball here of mass m, and the length of this stick here is L, and this here is so it moves on this circle path here. So the position at a given theta here, so this length here depends on the length L, and this is just theta times L. So the position at time t is, let's call it S of t, is given by theta of t times L. And therefore, if we want to describe the motion, we need to consider what are the forces acting on this guy also. What is the sum of the forces on this guy? So we know by Newton that the force is given by the mass times the acceleration, and the acceleration, so maybe first, acceleration is given by, so in general, in physics, if I have a function describing the position, then the first derivative of the function describes, with respect to time, describes the velocity, and the second derivative describes the change of velocity. In other words, it describes the acceleration, and therefore the acceleration a of t is given by the second derivative of the position, which in this case is L times the second derivative of the angle. And now by Newton, we know the forces at time t is given by mass times the acceleration, so this is m times a, and in this case we have the mass times at, so in this case it's m times L times the second derivative. Okay, so but now what's another way to describe the force acting on this mass here? Well, the main force acting on this is gravity. So for this, let's look at this thing here. Where is gravity in this picture? Well, gravity is the acceleration in this direction here, so given by small g. But what is the part of this acceleration on this ball here? So this can just act on the direction where the ball can actually move. So here we can draw a triangle. Oops. And we see that this angle here is also theta. And therefore this part here is given by, well, this is the sine of theta times g. So here we have, maybe this blue, sine of theta g. And the movement of this ball is going this, so for positive theta we assume the movement is like this. So the force acting on this ball here is in the opposite direction, given by the mass times this acceleration here. So in other words, this f of t is also equal to minus the mass times the acceleration we get from there. It's a gravity times the sine of theta, or more precisely of theta t. Okay, so in total, what we get is, equating these two things, we see that this equals this. So first of all, we can divide out the m. So in other words, this angle doesn't really depend on the mass. So if you put 100 kilograms there or 10 kilograms, it doesn't really change the movement. And therefore, in total, we have that L theta, the second derivative, plus, so these are equal, and therefore I can bring this on the other side, divide by m. So therefore I have plus g times the sine of theta t equals 0. And then we can also divide here by L, so this is g over L times sine of theta t. So now we have an equation involving this function we are looking for. So we want to describe the angle at time t, so this is the function we are looking for. And here we have the second derivative, and here we have the function itself, but we still have this sine. So this is not really a linear differential equation we considered in this course. But what we can usually do is, if this angle t is small, for example here in this picture it's not going crazy like 90 degrees, so if we assume that this theta is small, we have this approximation. So for small x, we have that the sine of x is roughly given by x. So if you draw your sine here, so this is a sine, and near 0, if you have the function x, so this is a sine, then for small values, this function x is a good approximation for the sine. So therefore, usually in a lot of applications where the numbers you are looking at are small, you can use that the sine of x equals x. So therefore, if we rewrite this, so for small angles, we have that the second derivative plus g over L, and now instead of sine of theta t, we just write theta t equals 0. And now we are in the situation where this is actually a linear differential equation with a linear differential operator t is given by d squared, second derivative, plus g over L, because here it's just the identity. And we are interested in the solution of this homogeneous equation. So in other words, we are interested in the kernel of this linear differential operator. And now this has a shape as follows. So this is d minus a squared plus b squared. So this is one of these types where we have these sine and cosine. So in this case, a is 0 and b is square root of g divided by L. So therefore, now let's go back to our theorem here. If we have a factor like this, so in our case now this m is 1, we get these two solutions here, e to the at times cosine bt, e to the at times sine bt. And in our case a is 0, so e to the 0 is 1. So we get that the solutions are given by linear combination of cosine bt and sine bt. Here. So, solution, or solutions, this theta of t is, I can choose some number c1, cosine of bt, so square root of g over L, t, plus c2, sine of square root of g over L, t. Okay, and well, and now we can, well, we get infinitely many solutions, but maybe a good starting parameter, so we can assume what happens at the beginning. So if I start with some math here, maybe we can assume that we get some starting angle theta 0, and maybe we also start with 0 velocity starting. I don't give it a push, I just leave it, and then I want to see what happens. So for example, if we assume that at time 0, maybe I have some starting angle, so this is the starting position of my pendulum, and I also maybe assume that the first derivative at start is 0, meaning I just leave it there and then see what happens. But I could also say I give it a push, so I start with some velocity, and then I would change this number here. And with this, so if I have these additional conditions, I get some conditions on these C1 and C2. So for example, if I plug in 0, then this part vanishes, and I want this to be theta 0. So this at 0 is 1. So this C1 is exactly this theta 0. So theta t is my starting angle, cosine of square root of g over L t, plus, and if I assume that, so if I take the first derivative, this goes to sine and this goes to cosine. If I plug in 0, then the sine part vanishes, and here I have cosine, and I want this to be 0, and therefore this C2 needs to be 0. So in other words, these two conditions imply that C1 is theta 0 and C2 is 0. So in this case, I get this solution here, and this we could plot. Let's take some nice color. So here we start at, so this is the time axis, and here we start with some angle theta 0, and here it's minus theta 0, and then it will be the cosine of this. Well, so you see that similar to this animation here, the angle goes from theta 0 to minus theta 0, theta 0 to minus theta 0, and so on. And we get this graph here. But of course this is not really, I mean, how you can see in this example here that this will stop at some time, because we also should increase some friction. And for this, what we could do is we could add another force here given by the friction, and the friction will depend on the velocity. So if I have it really fast, then I get more friction. So in other words, so let's make the color, the pink part, friction. So I would get some multiple of the first derivative here, maybe. So this would mean I get some derivative, first derivative here, and then this means I get some d here, and this would actually then lead to the fact that that this a is not 0, and this will be a positive number, so this a here will actually be negative. And what does this mean? Well, if we have this additional factor here, then e to the, of course we will also get a different b. So this b will not be just this, it will be just something else, depending on this friction parameter and this g over L. But the main point is that we will get a factor here, e to the at, where a is a negative number, and then in this case, if t increases, then e to the, let's say minus t for example, and this goes slowly to 0, and then we see if we would, so then maybe we get e to the something here, where a is negative, and then we would get, we start at theta 0, but then it will not go down to minus theta 0, but it will look maybe something like this, and then after a long time it will be actually 0, and this would correspond to, well, maybe this is a really bad pendulum, but you will see that it starts at theta 0, goes not exactly to minus theta 0, and then it goes slowly to 0. Okay, so I hope this gave a nice application of our of the things we did. And yeah, so this was the last lecture for this topic, but also the last lecture for this semester. Maybe next week we will do maybe some overview video, because maybe I shouldn't end in the lecture, in the unlucky lecture 13. But yeah, we will see in the tutorial. See you then.